Hi everyone, I'm Somrita. Today I'll talk to you a little bit about learning-enabled adaptation to evolving conditions in robotics. And so of course, I know I'm preaching to the choir here. Today we're seeing robots in more places. Of course, autonomous cars, which we'll hear more about soon. Also in the skies, in warehouses, and in surgery rooms. And so one thing that all of these robots have in common is that they're built off of this autonomy stack, right? Today I'll be talking to you mostly about the model piece, but I want to talk to you about how that kind of fits in to the rest of the autonomy stack here. So the model, we can think of it as taking in these observations X, and it's parameterized by some parameters theta, and you get an output prediction from this. This prediction is then used by a planner to generate a planner policy, and a controller translates that planner policy into these low-level actuations, which is how the robot will interact with its environment. And then raw signals from the environment are picked up by sensors to generate the observations, which is what will feed into the model. So that's kind of how this model fits in. Now, as roboticists, of course, we try to make this whole stack, and especially the model, as robust as possible and capture all of the conditions that we expect the robot might see during deployment. The reality, though, is that during deployment, there's often a change in conditions, whether that's for the environment or the robot, that we didn't predict and we did not expect. And we often need to respond in a timely manner, not just say, okay, something unexpected happened and move on, but we actually need to respond, maybe before the next communication or over the system lifetime. And so the very broad research question that kind of guides my PhD work is how can autonomous systems reliably adapt to these unexpected evolving conditions during deployment? And so today I want to talk to you specifically about one type of evolving conditions, which is shifted distribution. So when you have these kinds of distribution shifts, how can you adapt your model over time? And so we'll take a look specifically at adapting to outer distribution inputs, and as a case study, we'll use this data set of satellite images, and from these we'll try to estimate the pose of a satellite from these camera images. So that's kind of what the model looks like, is that we'll have some camera image of the satellite, and we're trying to predict its pose. So pose in 3D space, which means its position, x, y, z, as well as its orientation. So that could be its roll, pitch, yaw, or quaternions, however you want to represent that. And the reason why we want this model is because there's some downstream decision-making logic that might use this for trajectory tracking or autonomous docking with this satellite, something like that, or to clean up space debris. But let's focus on the model itself. And we know that this is true for a lot of learned models, that the performance of this model depends on whether the input that you're seeing is similar to what the model has been trained on. In fact, that's a mathematical assumption that we make, is that it's going to be IID, which is that it's going to be drawn from the same distribution. In reality, the distribution of inputs that you see can often change after deployment, especially if you're deploying this over a long mission lifetime. So you might start seeing things like Earth in the background or lens flares that you didn't train on originally. And so when you have these kinds of observations that come from a different distribution, we call them out-of-distribution observations. And these out-of-distribution observations can lead to incorrect predictions. And we care about this because that can lead to unsafe outcomes by the downstream decision-making logic. And so really what we're asking is, okay, we want this kind of lifelong deployment of learning-enabled components, but we know that the data distribution may change over time. So how do we adapt to that? So this is how I envision kind of the data lifecycle. I said lifelong deployment. What does the data lifecycle look like? You can think of this as a sequence of inputs coming in. In this case, they're images. These might be sequential. These might be batched. And then you have a model that outputs some kind of prediction. Here, that's the pose of the satellite. In addition to that, we often will have some measure of uncertainty. So there are various different techniques to do this, and these types of uncertainties are what we use to do out-of-distribution detection or runtime monitoring. And this by itself could be a whole, not just a talk, but a whole thesis. So out-of-distribution detection or runtime monitoring requires that we have some notion of the uncertainty of the model. What I want to do, though, is go a little bit further. I don't just care about detecting that something is out-of-distribution. I also want to be able to adapt to that. So I want to close the loop here. And how we're going to do that is we're going to select some of these to actually label, which means that we'll select a subset, we'll flag them and say, okay, these are not just out of distribution, but I actually want to generate labels for these. And then request labels. So this might look, for the satellite cases, you have to downlink this image to the ground and ask a human or some other oracle to actually label this for you. So this is an expensive process. And of course, then you use these labels to fine-tune or retrain your model. So now you can adapt to this distribution shift. So essentially things that were out of distribution will slowly become in distribution, and you can start to trust your model more on these kinds of inputs. And so this kind of forms the the 4 pieces of this idea of doing this data lifecycle management. And steps 1 and 2, we think you can do onboard your robot. So these should be computationally inexpensive. Steps 3 and 4, of course, are expensive, and you want to be very judicious with how you select your labels. And so this might be obvious, but I want to kind of drive home the point that the more images you flag, the more labels that you request, the more fine-tuning you do of your model, you're giving your model more information, and therefore you're likely to see better performance. But this comes at a cost, and so this performance and cost trade-off is something we'll come back to in a little bit. Okay, but let's kind of step through this. How do we even do this? Let's go through each part one by one. So first, let's talk about out-of-distribution detection or runtime monitoring. And so one way of doing this is to use Bayesian methods. I'm kind of just sketching out a much more involved algorithm here, but the idea essentially is you choose a prior distribution over your functions, you compute your posterior distribution given your training data. That allows you to evaluate the predictive uncertainty at your test points. And so essentially, if you've seen a lot of points that are close to what you're seeing now in the test data, you know that you're relatively confident or not as uncertain about those points, and vice versa for out-of-distribution points. So if you apply this kind of technique to a pre-trained deep neural network, you get the Scott algorithm. And I'll talk a little bit, just again, sketch out the Scott algorithm itself. And so what this looks like, let's see if I can pull up a pointer. Yeah, so offline what you're doing here is let's say you have some kind of model like this. And then what you'll do offline is you start with some prior on your weights. You have some prior distribution on your weights right here. Then you take your training data, or more realistically, a representative subset of your training data. You pass that through and update your posterior. So now you or update your belief to get your posterior on your weights. Using this, you can kind of construct essentially 2 things. One, your output, as well as the Jacobian, which is a linearization of your model itself. Now you basically have your distribution over your outputs, and the entropy of that distribution can give you a measure of your overall uncertainty. So this is one way of getting a scalar value of your uncertainty. So that's what Scott does. It gives you a scalar value of your uncertainty. So now the key idea here is that, okay, you can now detect out-of-distribution inputs by estimating the functional uncertainty and then thresholding the uncertainty value to say, all right, at this point we are in distribution. If our uncertainty is high, we are out of distribution. Let's take a look at that on a toy case. So first, this is like the MNIST data set where you have these handwritten digits and you're trying to classify what digit it has been written down. So during training, you might have seen digits like this. Maybe during deployment, this is a toy example, maybe you mix in some fashion MNIST images, things that don't look like digits. And you train a classifier and you add a Scott wrapper, and you see that you're able to detect the ones that you think are out of distribution. So this kind of matches our expectations. Again, though I said the focus of this talk is not about detecting that something is out of distribution, but adapting to it over time. So in order to adapt to it over time, we need to subsample these. Some of these I want to store and label, because I want my model eventually to not just do well on the digits, but also start to learn these new classes that we're seeing. In order to do that, I need to select a subset of them to label. It would be great if I could take every single out-of-distribution image, generate labels, and fine-tune, but that's a pretty expensive process. You wouldn't want to do that, for example, with an autonomous car where you have lots of frames that you're seeing. So how do you sub-select from this? Well, I said Scott outputs the scalar uncertainty value, so one reasonable thing to do is to just select the 2 in this case that have the highest uncertainty, right? So that's pretty reasonable. I would say that this looks okay. These are relatively correlated images. They're about the same shape. So maybe we can do better, but we'll come back to that. Let's look at this on the actual example that we were talking about with satellite pose estimation, where we have a training data set that looks like this. And then during deployment, we see some that are not from the same distribution. We ask God which ones are out of distribution, and the answers that you get are pretty much what you would expect. The ones that have a lens flare or Earth in the background are the ones that Scott thinks are more likely to be out of distribution. Again, though, what we care about is subsampling some of these so we can label them and retrain. If you use the ones that Scott thinks the model has the highest uncertainty on, you get these 2 images. And I would say that's great, but we're really missing out on something here. We're missing out on there are a couple of classes of OOD that we're seeing, and we're not able to really capture all of that by just asking what the model is most uncertain about. So can we do this subsampling more intelligently? So that's what I'll talk about next, is selecting a subset of inputs for labeling. So how should we do that? How should we select a subset of these out-of-distribution inputs now that we have detected them, so that we can store them and then label them, retrain our model? And what I propose is that we should ideally choose a diverse subset. So not just the ones we're most uncertain about, but the ones that we think are diverse, so that we are, one, being judicious about our bandwidth limitations. In this case, you can't actually downlink every single image that you see. but also we're maximizing the information gained to the model. And this is also correlated with an idea of novelty. A lot of times in robotics, you would want to capture the things that you see that are novel. And so the problem statement is, from a batch of M inputs, how do you select B inputs for labeling? Or more concretely, how do you select B diverse inputs for labeling? And so now, before we dive into the algorithm itself, we'll call this is diverse subsampling using SCOD, ds-SCOD. Before we dive into the algorithm, let's take a quick look at some of the math behind it. So consider that D0 is your training data set. Consider that DP is a full test data set, everything that you're seeing that is out of distribution or you've detected it to be out of distribution. Ideally, you would have your entire new test data set as well. If you could do that, if you could have your training data set and everything that you've added, this would be your full data posterior. So this is what I would ideally like to calculate. Or if you think of that in a log posterior form, what I want to calculate is this term here. So I want to be able to ideally calculate the posterior update as a result of choosing one of those inputs xi. Unfortunately, this is not computationally tractable. I can't actually calculate this. But I can kind of come up with these approximations. If I take one of those terms and look at the log likelihood of the data, so just this first term right here, I can approximate this with a second-order Laplace approximation that depends on the Jacobian matrix of how much your outputs change with respect to your weights and the Fisher information matrix of your output distribution. So these are things I can quantify and things that actually our out-of-distribution detection algorithm, SCOD, already does. So this is not exact, but we can kind of quantify our update for the ith input in these terms. Now, if we make that assumption, we say, okay, our update, if you pick the ith point, is this expression. Now, what is the update if you pick all of your endpoints? If I pick everything that was available to me, if I could do that, what would my update be? Versus what would my update be if I picked points according to some binary vector C, where C is essentially a sequence of zeros and ones. It's of length m, and only b of them can be set to 1. So essentially, which ones am I picking? What I want to do is minimize the loss of information. So I want to minimize the difference between the two. What I'm saying is, I'm only allowed to pick up to b. Which b should I pick so that I get as much information that is as close as possible to picking all of the m inputs. So I want to minimize the loss of information essentially here. So each element of C, like I said, has to be either 0 or 1, and up to b of them can be equal to 1. So that's all the constraints here. Now, there's a relaxation that makes this computationally tractable. Essentially, this lets you solve this using a Frank-Wolf optimization. You kind of form a kernel function, you relax some of your constraints, so instead of having these strict binary constraints, they're now non-negative constraints. But we'll skip over that for a second and kind of say, okay, there is a tractable way of actually solving this minimization problem. Okay, so now let's take a look. If the summary of the takeaways from this whole algorithm is just this, is that the kind of intermediate quantities, such as Jacobians, that you generated from out-of-distribution techniques, out-of-distribution detection techniques, you can reuse that as a measure of the information gain that you would get from each input. That's the point. The point is that not only can they tell you which ones are out of distribution, they also tell you they encode a measure of the information gain that you're getting. And then from an information theoretic perspective, we're just choosing the subset of inputs that collectively maximize your information gain. So let's look at some of those toy examples that we looked at before. So if you remember from the mix of MNIST and fashion MNIST data points, these were the two that we would get if we selected the ones that we were most uncertain about. If you now subsample for diversity specifically, we get things that I would say maybe look a little bit less correlated, slightly more diverse. Back to the satellite pose estimation example again. Initially, we were sampling by highest uncertainty, and I would say that the two that we were selecting were from the same class, the same type of auto-distribution. They both kind of have a lens flare, right? If you select for diversity explicitly, the sorts of things you start seeing start to sample from the different classes or types of auto-distribution, so you're kind of getting more information. Okay, so great, we've seen this qualitatively, but the real proof is quantitatively, does this work in the full data lifecycle? Does this actually result in an improvement? So now we'll request labels, and we'll retrain the model, and we'll do this over its full life cycle. So that's what we're asking, is, again, coming back to that idea of, like, in the full data life cycle, what is the trade-off now between labeling cost and performance? So as a reminder, this is kind of what I think of as the data life cycle. And what's changing here is just the images that each of these algorithms flag for relabeling. For each of these algorithms, we'll give them like a fixed budget, which is the number of labels that they're allowed to request. And that's the only thing that's changing here. They're still going through the same life cycle individually. Okay, so let's look at the performance versus cost trade-off. So on the x-axis, we'll plot the average improvement in model performance. I'll talk about improvement. On the y-axis is the labeling cost. So essentially, what percentage of out-of-distribution inputs am I labeling? Now, I'm benchmarking this against, let's say we label nothing. That's a black triangle down here. If you label nothing, even if you see out-of-distribution inputs, we're not going to label it. So we just have our baseline performance. Whatever we did during the original training, that's all we get. So that's our baseline performance, so 0% improvement in performance. And we're not labeling any of our out-of-distribution inputs, so we're at 0, 0, essentially. On the flip side, let's just say we don't care about the budget. We're just going to label every time we see an out-of-distribution input. No such thing as a budget. We're going to label everything. So that's 100% cost, and theoretically also the most information given to the model, so 100% improvement in model performance. And so with those two benchmarks, let's start thinking about ways to go in between. Rather than those two extremes, how about we start selecting randomly some of those out-of-distribution inputs? So between 5% to 75%, let's start sub-selecting some out-of-distribution inputs. And perhaps unsurprisingly, you see this kind of trade-off, right? So the more information you give to the model, the more labeling you do, the better model performance you get. We can be a little bit more intelligent. One of the things we proposed was to say, okay, let's use that measure of Scott uncertainty. So instead of just picking 5% randomly, let's pick the 5% that the model is most uncertain about, or the 75% that the model is most uncertain about. And you see that we do a little bit better. For the same labeling cost, we get slightly better model performance. And then if you start thinking about diversity, where we're actually explicitly choosing the 5% or 75% that collectively gives the model more information, we see that we do a lot better. For the same labeling cost, we get much better model performance improvement. In this particular case for this data set, we get performance comparable to labeling 100% of inputs while only labeling about 50% of them. The key idea I want to leave you with is that we've talked about a framework to evaluate that full data lifecycle. We've talked about an algorithm to select a diverse subset of test inputs. And one thing I just want to put out there is that we've also been developing this open source benchmark that is application agnostic to compare algorithms that do this kind of detection and adaptation to out-of-distribution inputs. Think about like 1 minute. In that 1 minute I have, I'll talk quickly about some other pieces of work that are being done in the lab thinking about this problem. So if you've been kind of following along, or if you're familiar with continual learning, you'll probably already thinking about, well, the more retraining you do, what do you do about forgetting your original data? This is a common problem, right? So you keep retraining on new classes, what if you forget your original data? And we've shown that there's ways of utilizing the same uncertainty estimates to help you generate a regularization term to kind of prevent some of that forgetting. We've also started thinking about, can we construct runtime monitors if you know the different things that might cause your out-of-distribution? So I've been talking about these different classes of OOD. Well, can you actually distinguish between them? Can you construct runtime monitors that distinguish between different classes of out-of-distribution? So we have some work there, and we're also talking about, we said that expensive piece in adapting to OOD is actually generating the labels. So how much of this can you do in the absence of labels, so in a self-supervised fashion? How much of this can you kind of do by just finding invariant features between in-distribution and out-of-distribution data? So the main thing I hope I've been able to convince you is that if you're going to want to adapt to out-of-distribution inputs over a lifetime, you would benefit from curating for diversity. But on that note, just happy to take questions.
I have one. Your abstract mentioned physics-based.
Yeah.
And here, I guess the physics is what?
So I actually ended up splitting my talk into two pieces and then discarded one of them. Sorry about that.
Okay.
But we can talk about that other piece.
Okay.
Some other time.
Very basic questions. When you were saying that adapting the model, so mainly what you are doing is changing the parameters of a fixed model, right? You are not changing the whole architecture of the model, right?
Not changing the architecture. So essentially updating the weight. So fine-tuning.
Just fine-tuning you are doing. But is it enough often? Because if the new samples are very different, you might have to just repair the model in a very different way rather than just tuning the parameters, right?
That's a good question. And it really depends on how severe your distribution shift is and whether your original model is expressive enough to capture your distribution shift. So you're right, and you would have to keep monitoring performance to see if that hypothesis is valid. In a lot of cases where things are just slightly shifted and you're seeing gradual shifts, you were trying to do something like pose estimation, you'd still be using a CNN, right? Yeah. All you really need to do is update your weights. It's still expressive enough, so this kind of method would work. But there are definitely cases where you're right, where it's a drastic enough distribution shift that you might actually want to completely retrain.
pair that smartly?
So I think one of the things you could do is kind of just keep track of your performance as you're kind of going along. And if you don't see a good improvement in performance by fine-tuning, you're probably going to have to start thinking about that. About maybe choosing a different model. I think some of that is also a little bit about knowing initially what your model is capable of, right? So if you're still dealing with the similar type of image inputs, if you're still dealing with similar predictions that you're doing, it's reasonable to assume that in those cases, it doesn't make sense to change your architecture.
But real world is full of surprises.
Definitely.
Thank you.
Which domains are more prone to distribution shift? I don't know if you've done some work on that.
Sorry, could you
Which
repeat?
domains are more prone to distribution shift?
Yes. So we've talked a lot about perception right here, and so I'll stick to some perception examples. I think a lot of autonomous driving companies think a lot about distribution shifts because, I've been told this anecdote is that, you think about training in rain. You go out in San Francisco, you train in rain. But then rain apparently is a little bit different in each city, depending on the size of the raindrop and the type of humidity in the atmosphere. So that itself is just a distribution shift. You've trained on rain, but you try doing the same kind of rainy weather driving in a different city. That's a distribution shift. You can overcome it by just, training with that, but that's a type of distribution shift. I think the ones that are maybe more common and people think about are like changes in lighting. So, that forms a distribution shift. One that a lot of people care about also is sensor degradation. So as you have the same sensors out in the field for a while, your sensors can degrade over time, and that will change slightly what your image looks like. Or you might just have slightly different configurations of sensors. You might mount your sensors slightly differently, and that can affect a perception module. That little bit of drift and exactly where the sensors are mounted can form a distribution shift, and these are things you would want to adapt to. But just some ideas only in the perception field. We can talk about other modules as well.
Well, thank you
I
very much.
had a question. So that
one
your
more, yeah,
diverse
come on.
SCOD, it happens entirely at the edge on the, okay.
Yes, we intended to be on this.
And you have some GitHub stuff where, because there's a number of nice active learning libraries, and it'd be nice to give this a whirl.
Yeah.
Yeah.
Would love that. Great. Thanks, Marcus.